Have you ever looked at an ultrasound image and just thought, how? How is that even possible? A live video feed from inside a person's body. Well, today, we're going to pull back the curtain on this incredible technology. We're going to follow a single tiny pulse of sound on its amazing journey from a machine into you and back again to paint a picture.
I mean, really think about it. How can this simple probe with a little bit of gel show us a living, breathing, moving world that's otherwise completely invisible? It honestly feels like magic. But it's not. It's a brilliant mix of some fundamental physics and some seriously clever engineering. So to really understand how it works, we're going to follow the life of one of those sound pulses. From the second it's created as an electrical signal to the moment it comes back as a faint echo, we're going to track its path step by step and see exactly how that amazing image gets made.
But before we get all technical and dive into the guts of the machine, let's start with what we can actually see on the outside. The stuff the doctor or the sonographer is actually touching and looking at. So your typical ultrasound machine has a few main parts. You've got the big display screen, that's obvious. Then there's the control panel, which looks kind of like a spaceship cockpit with all its knobs and switches. And of course, you have the transducer probes. These are the real stars of the show. The whole thing is usually on a cart with wheels so you can move it around easily. And yep, sometimes the hardest part of the whole procedure is just finding the on-off switch. Okay, let's get into it. We're now going inside the machine, right to the beginning. Where does our sound pulse's journey actually begin? We're going to use this diagram as our roadmap. Think of it as a "you are here" map for our pulse. And our first stop is what's called the front end. This is the main gateway for every single signal, whether it's going out or coming back in.
Now, here's the first big surprise. The journey doesn't start with sound at all. Nope. It starts right here, in the front end, as pure electricity. A component called the transmitter creates these perfectly timed, high-voltage electrical zaps. A computer is controlling this whole process with incredible precision, setting the stage for everything that follows. All right, so we've got our electrical pulse. Now it gets sent to what is probably the most critical and definitely the most recognizable part of the whole system, the transducer. This is where the real magic starts to happen.
Let's check our map. That little electrical pulse has now arrived at the transducer. That's the handheld wand that the operator places on your skin.
Honestly, the best way to think about the transducer is that it does two jobs. First, it acts like a loudspeaker. It takes that electrical pulse and converts it into a high-frequency sound wave that it sends into your body. Then, in an instant, it switches roles and becomes a super-sensitive microphone, listening for the faint echoes of that sound as they bounce back. It's both a mouth and an ear, all in one.
So you've probably noticed that not all ultrasound images look the same, right? Some are rectangular and others are shaped like a wedge or a slice of pie. Well, that's not just a style choice. It's determined entirely by the design of the transducer and the specific job it needs to do. Let's look at the two main types. On the left, you've got a linear array. It has a big, flat surface and it sends sound beams straight down in parallel lines. That creates a nice, wide, rectangular image, which is perfect for looking at things just under the skin. But on the right, you have a phased array. It's got a tiny footprint. Instead of sending beams straight down, it cleverly steers them from a single point, fanning them out to create that pie-shaped image. This is absolutely essential for things like looking at the heart, because it lets you peek right between the ribs. So the transducer has done its double duty. It sent the sound out, and it's converted the returning echoes back into very weak electrical signals. Now, those faint little whispers are sent off to the brains of the operation to get processed. Back to our map, that signal has now traveled deeper into the machine, entering the section we call the scanner. This is where the heavy lifting and complex processing really begins, starting with a piece of hardware called the beamformer. The beamformer is amazing. Think of it like the conductor of an orchestra. Inside that transducer are thousands of tiny crystals, and the beamformer tells each one precisely when to fire, down to the nanosecond. By organizing them perfectly, it gets them all to sing in harmony, creating a single, focused beam of sound. It pulls a clean, coherent signal out of a sea of potential noise. Now, as sound travels deeper into the body, it naturally gets weaker and weaker. That means echoes from deep down are much quieter than echoes from right near the surface. That's where time gain compensation, or TGC, comes in. It's basically a really smart volume knob. It automatically cranks up the amplification for those deeper, quieter echoes, making sure the final picture has a nice, even brightness from top to bottom. And the high-end systems have even more tricks. like something called spatial compounding. Check out the difference here. On the left is a conventional image, taken from just one angle. It's okay, but kind of grainy, right? Now look at the right. That's a compounded image. The machine took pictures from multiple angles and stitched them together. Bam! The speckle noise is reduced, the edges of the tissue are way clearer, it's just a much, much better image.
Okay, at this point, we've got clean, amplified, and perfectly organized data. But it's still just a bunch of data representing hundreds of individual lines. How in the world does that become the actual picture we see on the screen? Our pulse is at the very last stop on its internal journey. It's arrived at the back end. This is where all that hard work finally gets turned into an image.
So the data that's coming in is organized by direction and depth, kind of like the spokes of a wheel. But a video monitor is just a simple grid of pixels. Scan conversion is the crucial final step that translates that spoke data into the grid data the monitor understands. It's like a digital artist painting by numbers, filling in all the gaps to create the smooth final picture we're used to seeing. And you gotta remember, this entire journey from electrical zap to finished picture happens dozens of times every single second to create what we see as live video. It's mind-bogglingly fast. And of course, the technology didn't stop there. The next big leap was moving beyond those flat 2D slices into full 3D volumes. Modern machines can grab a whole chunk of data at once, allowing them to build a complete 3D model of an entire organ or, most famously, a developing fetus. So what's 4D imaging? You hear that term thrown around all the time. It's actually really simple. It's just 3D with the fourth dimension, time, added in. You take that amazing 3D model and you hit play. And now you're watching a structure move in real time, like seeing the tiny valves of a fetal heart opening and closing. It is an absolutely breathtaking jump in what doctors can see. So we followed the journey from a simple electrical pulse to a sound wave to a faint echo, all the way back to a real-time 4D video of a beating heart. It's just a remarkable process, and it really leaves you with one big question. As this window into our own bodies gets clearer, faster, and more detailed, what new mysteries are we going to be able to solve next?